All right, now that we've got an expression for surface area, let's go ahead and work some examples. So why don't we return to the cone that we had a little bit ago and see if we can't compute a surface area. I have to cut the cone off at some point, otherwise the surface area is going to be infinite, so I'm just choosing to consider the part of the cone that lies below the plane z equals 3, like this. So what is the area of that surface? All right, well, we have a couple different parameterizations of this cone, as you might remember. I'm going to go with the one that we borrowed polar coordinates to do. So we had u and v as the parameters, and we were borrowing our usual parameterization of a circle to get the x and y rotating. And then it turned out that, well, a couple different ways to look at it, but since z was the square root of x squared plus y squared, it was forced that z would be the parameter that's representing the amplitude of the cosine and sine waves for x and y. All right, and so if I want to choose the appropriate parameter space to sweep out exactly this part of the cone here, then v is going to go from 0 to 3, because v coincides with z in the picture. And then u needs to go the full circle, so we'll make it 0 to 2 pi. So our parameterization then is this vector function. And now we can compute the integrand of the surface area formula. So I'm taking partial derivatives with respect to u and v of each of the component functions. Okay, and what I'd like to do to take a cross product, because that's what I need for the integrand, once I've stacked these two vectors on top of each other, I can sort of just read off the cross product, imagining these in a larger matrix. Okay, and simplifying, and I'll take the magnitude so that I'll have the integrand. Okay, and now we're ready to set up our integral. We integrate over the region in the parameter space, which here is sort of a rectangle in the UV plane. And then we just place in here the appropriate integrand. This is the magnitude of RU cross RV. And we integrate over the parameter space, du dv. Okay, and I've gotten 36 pi for the surface area. Okay, in this next example, we're going to, again, practice this surface area formula, but the surface that's described is a little bit complicated. It's going to take us a little bit of thought to even set up a parameterization. Okay, so I'm going to form like a football surface by starting with a curve, and the curve is described in the xz variables. So I imagine this curve in the xz plane first. So x is cosine z. That means it would look like this. And I only want the part of the curve that goes from negative pi over 2 to pi over 2. So I start with that curve, and in 3 dimensions it looks like this. And I'm asked to rotate this thing around the z-axis. So I kind of have to spin it around like that, and since they told me it was a football, I'm going to make it look like a football. Okay, so that is the description, and I somehow from this have to come up with a parameterization which is going to be a representation of the points on this surface over some parameter space uv, and we'll have component functions depending on u and v for all x, y, and z. So I kind of just have to think about this for a second. It's a little bit tricky. So for example, if I take a point on this surface, I want to think about what its components are going to be. Well, it's going to have a z value that's in between negative pi over 2 and pi over 2. And both the x and y coordinates sort of depend on what that z value is. Over here, when y is 0, I know precisely what's happening with that dependency. When y is 0, that was the original blue curve that I drew. The x-coordinate is exactly cosine of that z value, and the y-coordinate is 0, right? But as you move around the surface, x is no longer perfectly cosine z, and then y, gains some dependence on the z value. But here's a useful geometric observation. If I connect, I draw a line from that point to the z-axis like this, and really what I'm doing is I'm drawing like the r value of that point, where r is the polar coordinate, then I see, I already know that r squared equals x squared plus y squared. And I see that at any given point on the surface, if I draw that r value is depending on z, just as the x-coordinate depends on z in the xz plane over here. So what I'm saying is if I draw that r coordinate, r is cosine of the z value. Because it's precisely this relationship here rotated. So knowing the dependence x on z actually gives us the dependence r on z, because it's simply, r is like the rotated x value around. So this is key right here. Okay, so just in polar coordinates, I'm reminded that, I can express r in terms of x and y like this, and I can also express x and y in terms of r and theta, right? So if I put these two things together, the fact that r should be cosine z and x and y should be r cosine theta, I get myself two-parameter parameterization of this surface. So let's put these things together, and I'm going to go ahead and switch our variables from r and theta over to u and v. Sorry, I'm going to switch the variables from z and theta over to u and v. Okay, so here is the parameterization. Again, it's a bit tricky, but let me go through it again. I looked at geometry carefully and decided that as I sort of take any point on this football, the r value should be cosine z, because the r value can be imagined as the x value in this picture just rotated around. And then I remembered that the r value is a polar coordinate, and x and y depend on that r value in the following way, where theta is our usual polar coordinate, sort of spinning around the x-axis. And I'm just for no great reason, but I'm replacing z with u and theta with v, just so our parameterization sort of looks like the same variable system that we've been using for parametric surfaces. So the u is acting like the z value, right? And the v is acting like the theta value. So I've put the parameterization into Grapher just to confirm that I'm getting something reasonable. This indeed looks like the x equals cosine z curve rotated about the z-axis. So since z goes from negative pi over 2 to pi over 2, my u is ranging between those values, and then v is acting like theta, so I have v going from 0 to 2 pi. Okay, so with that, I've got my parameterization, and I can set up the surface area expression. So let me just write out RUV and take a couple partial derivatives. Okay, and as before, since I have the RU and RV stacked, I'm going to go ahead and take the cross product below. Okay, there you go. So I've taken the cross product of RU and RV. I factored out a cosine U, and I used the fact that cosine squared V plus sine squared V is 1 in the K term. So here is the magnitude of that cross product, and now I can set up my integral for surface area. And as usual, I checked to see that I typed it in correctly and it interpreted the integral as I wanted it to. And, oh yeah, so this integral here seems to be the same as this. And so my surface area is around 14.5. All right, let's practice our formula again. I am asked to find the surface area of a portion of the z equals x plus y squared surface over this triangular region in the xy plane. I just graphed it just so I could get a visual of what this surface looks like. Okay, fine. And I'm not taking, obviously, the whole surface that would have infinite area, but I'm going to restrict my attention to a triangle in the xy plane. Now, remember, when z is a function of x and y, there's a kind of a cheap parameterization that I can construct. So if you remember, letting x be the parameter u and y be the parameter v, and then z, whatever function of u and v you get from that, that's what I'm calling a cheap parameterization, right? And so I can then express this region in the xy plane as a region in the parameter space. So what I'm doing here is letting v range from 0 to 1 and u range from 0 to v. And then I set up my double integral for the surface area. Oh, I better write out my parameterization and its partial derivatives, right? Okay, so here we have our double integral representing the area that's asked about. The region was set up as sort of like a type 2 region, and that was nice. If you take a look at this integrand, I wouldn't want to integrate with respect to v first necessarily. U is a little bit easier. So you see now all I need to do is a substitution to compute this integral. Okay, that looks pretty good.